Welcome back. In this module, we'll talk about a specific example of control and data plane separation called the Routing Control Platform, which uses the Border Gateway Protocol as a control channel to control the forwarding decisions of routers inside an autonomous system. We'll start by looking at various problems with BGP, and then we'll talk about the details of the Routing Control Platform itself. The Routing Control Platform is an early example of control and data plane separation, and the design of the Routing Control Platform talks about three deployment phases, ways that we get from present-day BGP to a complete deployment of the Routing Control Platform, or RCP, across multiple ASs in the Internet. In this lesson, we'll talk about each of these phases, as well as applications that become possible at each stage of deployment. It probably comes as no surprise that there are many problems with BGP. It converges slowly and sometimes not at all. It causes routing loops. It's misconfigured frequently, and certain network management tasks like traffic engineering are very difficult. On the other hand, fixing BGP is pretty hard. Various people have proposed incremental fixes, but some of those fixes make BGP even more complicated than it already is today. Other approaches have proposed completely new architectures and interdomain routing protocols, but the deployment of those architectures is almost impossible. The fundamental problem with BGP is that the AS is the logical entity for interdomain routing, but the BGP state and logic are decomposed across routers. So no router has complete BGP state, and each router makes routing decisions based on a partial and incomplete view of the state across the entire autonomous system. BGP also interacts in odd ways with other protocols, most notably with the IGP, or Interior Gateway Protocol, that runs inside an autonomous system. By contrast, the Routing Control Platform, or RCP, represents an AS as a single logical entity. It operates on a complete view of an autonomous system's routes and computes those routes for all routers inside an AS. The routers themselves no longer have to compute routes. In a complete deployment of the Routing Control Platform, each AS's RCP communicates routes with RCPs in other ASs. But there are incremental deployment phases that allow a single AS to deploy an RCP and still gain some benefits. One of the problems with BGP is that configuration state is decomposed across the routers inside a single autonomous system. So representing a single coherent network-wide policy is quite difficult. For example, consider the implementation of a simple policy such as don't advertise routes learned from UUNet to Sprint. In this case, the configuration is decomposed across routers inside the AS, so the routes themselves must carry state. In the first portion of the configuration, routers assign routes from UUNet by tagging the routes at the ingress router C. In a separate part of the configuration at router A, there's a separate part of the configuration that looks for that particular tag that was set at C and implements the appropriate filter to ensure that that set of routes are not re-advertised to Sprint. This simple policy is decomposed across multiple routers, making configuration relatively difficult. By contrast, the RCP centralizes configuration. It implements policies for the entire AS. It knows about sessions to all other ASs and implements policies in terms of the relationships with those ASs. This results in much simpler configuration since the routers themselves don't have to tag routes with state. Another problem with BGP is that it interacts with underlying protocols in strange and unexpected ways. In this example, the router inside the AS, C1, learns a BGP route to some destination, D, from R1, and C2 learns a BGP route to the same destination from router RR2. Because of the way the IGP weights, shown with numbers here, are configured, C1 will send traffic to D via the shortest path to RR1, which is via C2. C2, on the other hand, sends packets to D via a path that traverses both C1 and RR2 because the shortest path to the route it learned via RR2 is via C1. This particular configuration results in a persistent forwarding loop between C1 and C2, each of which think they must forward the traffic to D via the other. The forwarding loop results because no single router has a complete view of the autonomous system state. On the other hand, the RCP can compute routes with complete information. The RCP learns all externally learned routes and computes consistent router-level paths across the entire autonomous system. As a result, there's intrinsic loop freedom and convergence, and RCP actually doesn't even have to stick to the default decision process. It could even pin paths for traffic engineering and other purposes by setting up custom paths between routers inside the AS and any egress router. While these features are appealing, of course an important question remains of how we get from here to there. In other words, how we get from the situation where all of the routers are running IBGP with one another, making independent decisions, to a state where the RCPs are making the decisions and communicating the BGP routes with one another across autonomous systems. There are two issues to consider: backwards compatibility and also the incentives for any single AS to deploy an RCP. We'll tackle the challenges of deployment by proceeding in three phases. In the first phase, only a single autonomous system has to deploy an RCP. Before phase 1, we just start with conventional IBGP. Afterwards, a single RCP learns the best IBGP routes and IGP topology inside a single autonomous system. In this situation, only a single AS deploys RCP, but that single AS still gets the benefits of that deployment. An example application of this limited deployment is controlling path changes. For example, as we know in BGP, routers take routes to the nearest exit or egress via the shortest IGP path. So for example, router C might take a path on the left to router A, but if that particular link fails, IGP weights will change, and the shortest path from C to the exit A might increase. What we don't want to have happen is for that path from C to leave via a different egress, for example via B. In standard BGP, there's no way to change that because C would always choose the route to the nearest exit. But the RCP can pin egress points even as the IGP weights change, ensuring that all of the routers inside the AS continue to select A as the egress router even as links fail and internal topology changes. In the second phase, a single AS can not only control routes inside its AS, but can implement AS-wide policy based on all the eBGP routes it learns from its neighbors. This requires an additional deployment step whereby the RCP must learn not only all of the internal routes, but also the eBGP routes from its neighbors. So it must have additional eBGP sessions configured. One particular example is efficient aggregation of IP prefixes. Let's suppose that two egress routers each learn a less specific prefix and a more specific prefix that's contained inside that larger prefix. In this case, a router inside the autonomous system might want to aggregate these two prefixes since they overlap, but neither of the routers inside the AS know whether it's safe to do so, because it may be the case that some routers need to forward traffic to a specific exit point based on the more specific route the egress router learned. On the other hand, an RCP can determine which routers need more specific routes and which routers can get by with less specific routes. In this case, for example, the RCP can determine that it's not safe to aggregate because a downstream router will make different decisions about where to forward traffic to different egresses based on those more specific prefixes. In the third phase, all ASs have RCPs deployed, and the RCPs communicate with one another via some inter-AS protocol, which might not even be BGP. An application of this third phase of deployment is more flexible routing through better network management and various protocol improvements. Once RCPs are talking to one another, it's possible to replace BGP entirely. So there is a very broad range of applications that could be deployed in this third phase. In summary, the RCP embodies two principles for interdomain routing. It treats NAS as a single logical entity, allowing it to compute consistent routes using a complete AS-wide view. By acting as a central control point for the AS, it can also control various routing protocol interactions that were previously difficult to control. The separation of routing and control allows for simpler and more expressive routing configuration, intrinsic robustness by avoiding forwarding loops and enabling faster convergence, and the ability to enable new applications and innovations, including the opportunity for new types of traffic engineering applications.